Thank you very much, Walter, for the nice introduction. And first of all, of course, I would like to thank the organizers, Thomas, Laura, and Elio, for putting together this wonderful conference that we are all enjoying very much. And today, what I would like to do is to discuss the microscopic nature of possible emergent correlated phases in two-dimensional van der Waals bilayer platforms. So what we are interested in is, on the one hand, on bilayers of two different type of structures. So what we want to do is to bring together Mott insulator. Well, let me see whether I'm getting the right one. That was not the right one. That's the right one. So we want to bring together a layer, a monolayer, which is a Mott insulator in proximity to a metal semiconductor, and then search for what kind of correlated phases emerge out of this bilayer system. And the second type of systems we want to do is indeed what happens when we twist two monolayers of the same kind, what kind of correlated phases emerge. So some examples of this type of heterostructures or twisted structures are here given in the top of the slide. So on the one hand, we have now there's a lot of studies on this type of heterostructures where you take a Mott insulator, alpha ruthenium trichloride, which is a Kitaev material. So it's a system that shows, in fact, you have very well-defined magnetic moments on a honeycomb lattice, but the interaction with these magnetic within these magnetic moments is it's a spin anisotropic type of interaction, and in fact it has signatures of Kitaev physics. So what happens when you bring this Mott insulator with well-defined magnetic moments in proximity to graphene? And when you do that, and in fact I have to say that here in the Max Planck Institute in Stuttgart, this was one of the first places where these type of structures were synthesized in the group of Marco Buchard. And it's very interesting what happens here. So we have been studying these materials, and it seems that you get a kind of Kondo emergent physics. But I'm not going to talk about this system today in interest of time. What I would like to do today is to talk about another very interesting heterostructure where you bring together, again, this is in the systems, in these Tantalon disulfide systems, where you have different types of polymorphs, the 1T and the 1H. And there are very recent experiments where they built, so by molecular beam epitaxy, they built heterostructures of 1T tantalum disulfide, where in the system at a temperature of 300 Kelvin, the system undergoes a charge density wave transition and forms these so-called Star of Davis, 13 tantalum atoms, they distort in a Star of Davis fashion. And what we have at the end of the day is very well localized spins at the center of these Star of Davis, and they form a well-defined triangular lattice of magnetic moments. And this system, this monolayer, is a Mott insulator. And now we bring this system in proximity with tantalum disulfide in the 1H configuration, where here the system is a conductor. And we want to investigate what kind of behavior is observed out of this type of bilayers. And in the second part of my talk, I would like to discuss about magic angle twisted bilayer graphene. Of course, we have Pablo in the audience, so I don't have to say much about these systems, but what is very interesting is all this flurry of correlated phases. And very recently, there has been a lot of discussion whether these correlated phases can be understood in the context of a heavy fermion type of behavior. And this is what I'm going to do in the context of the topological heavy fermion model that was suggested by Sida Zong and Andrew Bernevik. So before starting, let me first acknowledge my collaborators in this work. So the number of collaborators have been increasing and increasing, but basically this is a collaboration between Frankfurt, Hamburg. Gautam is here in the audience. Würzburg, Lorenz is also here in the audience. The Weizmann Institute, Hyunku Bai and Bin Hayan, Igor Mazing, Andre Bernabik, who will come today. I don't know whether he's in the audience, but he said he would be today here. He has a talk, and his postdocs, as well as Alexei Zvelik, Antoine George, and Luca Di Medici. I don't have a photo, but he's our next speaker. So what we have been doing about these systems. So let me start with the heterostructure. And I will try to go step by step in order to understand the physics of this system and the interpretation of the experimental observations. So as I was mentioning, tantalum disulfide, these are van der Waals systems, and they grow in different types of environments. So we have the so-called 2H tantalum disulfide, where the tantalum is in a trigonal environment of sulfur. And this system, in fact, shows a charge density wave, a 3 × 3 charge density waves, but it's always in a metallic state. So in fact, it's a conductor. However, when the system grows in the so-called 1T configuration, in the 1T configuration, the tantalum is surrounded by an octahedral environment of sulfur. In this case, this system undergoes a charge density wave, as I was mentioning, at high temperature, where we have a distortion, as you can see here, of the nearest neighbor tantalums forming the Star of David. And what happens then is that it forms a molecular type of orbital, and what is left is the orbital of this tantalum at the center, which in fact it defines a very well localized moment. So what we have is a triangular lattice of this one electron per Star of David. And in this case, the system, because the hopping is so the bandwidth is much smaller than the Coulomb repulsion, this system is a Mott insulator. And in fact, because we have a triangular lattice of these very localized moments, there is a discussion whether the system is showing a spin liquid type of behavior. So there is, for instance, this recent work by the group of Eugenio Coronado in Valencia, where they claim to observe indeed this spin liquid behavior in these monolayer systems. But what I'm interested now is in bringing these two systems together and forming a bilayer. And this is what has been done experimentally by various groups. And here I'm just showing some of the experimental results, and let's see what it is observed and how we interpret that. So what I'm going to maybe describe in more detail is the experimental measurements by Vano and collaborators in Aalto in Finland, where what they did is they grow these bilayers, 1T, 1H, on graphite, and basically they do then STM experiments. And by putting the tip on, depending on which layer they are putting the tip, they observe a different behavior. So, for instance, when they put the tip only on the 1T monolayer, that's what they observe, basically a Mott insulating behavior, because this is the one where we have the localized moments. When they put the tip on a 1H monolayer, then the system goes, it's metallic, so shows this metallic behavior. And in fact, they are discussing also at the temperatures that they are measuring, whether they go into the superconducting phase. But now what is interesting is when they really put the tip on top of this bilayer. So here is 1T over 1H, and that's a spectrum that they observe. They clearly observe here at a zero bias peak, which they have been describing as a Kondo type of peak. And if you see here the temperature dependence of this behavior, it really shows going to lower temperatures, the presence of this zero bias peak. And these type of results have been, in fact, corroborated by many other groups, even also by taking the selenide. And even if you take the 4HB tantalum disulfide, which is a crystal, which indeed is built of 1H, 1T, 1H, these are experiments by the group of Chaim Beidenkopf at Weizmann, where they also observe this type of behavior. So the question that we have is, which is the origin of the zero bias peak. Is it really a Kondo type of resonance that we are seeing here? Because in principle, what we have is this layer of well-defined magnetic moments in contact with a conduction layer. So are we seeing here the physics of screening of the conduction electrons of these magnetic moments and then the appearance of this resonance? That's the kind of interpretation that has been given up to now. However, what I want to show you that this is more subtle than that. And why is this more subtle? Because of the following. So let me start now indeed going to the electronic structure of these systems. And then first I will do it in the context of a density functional type of calculation. And then we will go on including correlation effects by going beyond DFT. So first of all, what we see is, and we know whenever we put two layers of different type of structures, we have always to consider where are their relative chemical potentials. So which are their work functions? And depending on whether the work functions are very different, we're going to expect charge transfer. And this is what is happening here, that we have that the chemical potentials of these two layers are very different. So when you build up these bilayer structures, there is a charge transfer from this 1T layer to the 1H layer. And of course, this charge transfer is going to depend on the distance that you have between these two layers. The more near you bring the two layers to each one at a given distance, you will have a complete depletion of this correlated band. So all the charge goes into the 1H. And you will also have, of course, effects of hybridization between the two layers. So let's try to understand now this picture, but doing now a real calculation of what is happening to the electronic structure. So if we look here at the electronic structure, now you take, so this is the type of simulations that you can do very well within density functional theory, of course, by including the corresponding van der Waals corrections. These are results by CNQM2023 in Weizmann. And what one observes is that if you relax, you can basically, you take a real big supercell, and then you relax the structure by including all these contributions, is that the distance between the two layers is this that you find is the distance that it is observed in the 4HB, so in the crystal, the 4HB Tantalon disulfide. And at this distance, what happens is the following. What I'm showing in gray is the electronic structure of the 1H layer, and in blue is the electronic structure of the 1T layer. And as you can observe at the Fermi level, you only have the conduction electrons of the 1H layer. You have a complete charge transfer from this 1T layer to the 1H layer. And you can observe that because this is the flat band of this tantalum in the middle of the Star of David, which is completely disoccupied. So in this sense here, you have a conductor, and in fact, the 4HB is a conductor. At very low temperatures, it goes superconductor. However, now you start to consider different distances, and these, in fact, in this MBE type of growth, did they have different distances? In the distance, for instance, of the outer group that at least they claim to observe to have is about 7 Armstrongs. So it's really further away of this optimal distance in the crystal. So what happens when you start to separate them? Of course, the charge transfer is going to only be partial. And that's what you see, observe here at, for instance, 7 Armstrong, that you are having, and here what I'm showing is spin polarized calculations just to show the feeling, you start to having indeed that your d electrons of the tantalum of this layer are at the Fermi level. So we start here now to having a flat band at the Fermi level. And of course, we also have hybridization between the 1T and the 1H. And this is the situation we want to understand. So just to show you the evolution as a function of distance of this electronic structure, we go at the distances of the crystals, so 5.5 angstroms. This, I'm showing the partial density of states only of this correlated band. it goes to being empty and to being partially occupied. And now what we want to understand is what happens in this region, which is the region of the experiments, because this is now where we want to get information about this resonance peak that was appearing, which is the origin of this resonance peak. Because we have now two sources of screening of building this resonance peak. One is the fact that we have indeed this hybridization between the conduction electrons and the local magnetic moments, the local spins of the 1T. But because we have had this charge transfer, we also have popping within the 1,2 layer. So we also have screening due to the other 1T electrons. So how do we investigate that? So we are going to do that by including dynamic correlations a la the MFT. And it's very nice that Walter is our chair today, because he's, in fact, this was a pioneering work in this direction of the development of dynamical mean field theory. So now what we want to do is to try to understand the origin of the screening in the system by considering a model that we extract from these DFT calculations that includes, on the one hand, the Hamiltonian of the T electrons, so the kinetic energy, plus, of course, a strong Coulomb repulsion, and then, of course, the Hamiltonian of the H electrons, which contains the kinetic term. These are conduction electrons, so the only contribution that we consider from them is kinetic energy and the hybridization with the T electrons. And now what we are going to do is to treat this interaction dynamically by considering dynamical mean field theory. And one quantity that is very useful that one can calculate within this method of dynamical mean field theory to understand the screening of these 1TD electrons, one quantity that is useful is indeed the spin susceptibility. And this is what I'm showing, the spin susceptibility of the system as a function of temperature. So what is the spin susceptibility? So what we are doing is indeed calculate these correlation functions and then integrate over the imaginary times. So the information that we obtain is the following. So here what I'm showing is this susceptibility, so the spin susceptibility at the quarter field band, which means in the situation where we have a charge transfer of 0.5 electrons to the 1H. So this is the feeling that we have in the 1T. And now what I'm showing here is how this susceptibility behaves as a function of different hybridizations, where these 60 millielectron volts is the real hybridization in the system. So the straight lines show the susceptibility behavior that you would expect if your magnetic moments wouldn't be screened. If they are not screened, you are going to expect a type of Curie behavior. However, if you observe these are the data of the calculation, for any of the hybridizations, even by very small hybridizations, there is a strong deviation from this Curie law, which is telling us that there is a screening, important screening, that already comes, in fact, from the fact that they have a large charge transfer in this system. So the screening seems to come more from the charge fluctuations than from the hybridization with 1H. Now, just for comparison, let me show you the case that there wouldn't be any charge transfer, so that we had really a half-filled 1T layer interacting via hybridization with a 1H conducting electrons. What one observes in this case, in this situation, is that at the realistic hybridization, there is no screening. So the hybridization with the 1H in this system is not enough to show the screening effects that are being observed experimentally. So now how do we then interpret that? So in order to compare with the experiments, we have to calculate the spectral function. So this is the local spectral function as a function of frequency. So this would be the Fermi level. And here it is shown for the hybridizations that we have in this system and with the corresponding charge transfer. So we have a quarter field Hubbard model in this sense. And what one observes is that there is, as a function of temperature, the appearance of this resonance with very asymmetric lower and upper Hubbard band. And if we compare with and just for comparison, if we were to have no charge transfer, as it was assumed in the experiments, as you can observe, the hybridization is not strong enough to really build up this resonance at omega equal to 0. So let me compare these calculations with the observations from the STM experiments, where you observe as a function of temperature, this blob, and then going down in temperature, there is the appearance of this peak with asymmetric lower and upper Hubbard bands. So we suggest that one has to be very careful in interpreting this data, since there is a real charge transfer in the system. And in fact, what we are having here is more physics of a heavily doped Mott insulator than a condo type of system. And on the other hand, this is very interesting physics, because we don't know in, let's say, in the usual inorganic systems, any of them where you can really dope, go into this one quarter field. So this type of heterostructures give you a new platform for manipulating doping in a strongly correlated system as a function of distance between the layers. So you don't have to dope. It's enough that you control. I mean, maybe Pablo can tell me whether it's easy or it's difficult, but indeed controlling this distance between the layers, you can build up, in fact, you can find new phases due to the fact that you are doping a Mott insulator. So now let me go to the second type of systems, where we want to investigate also the nature of the correlated phases, where here we have a different situation. So here we don't have an heterostructure with this concept of a charge transfer. What we have here is now that due to the twist angle, we are creating these very flat bands. And the question is, and has been, whether the physics that some of the physics that is being observed can be interpreted in terms of a heavy fermion picture. So in fact, there was for some time the apparent contradiction that by looking at the observation in STM experiments, one was observing a lot of features of correlation and localization, while in transport experiments one is observing a lot of features of delocalization. And the question is how you bring these pictures together. And this was the proposal that you may be having here physics of heavy fermions, where in the magic angle twisted bilayer graphene, for instance, as is shown in this schematic in this picture, in these AA centers of the triangular lattice, you have well-localized states, which are hybridized with delocalized states, in analogy to what you do or you have in a heavy fermion system. So within this context, there has been the proposal by Sida Zong and Andre Bernebik of a topological heavy fermion model. And this is the model I would like to analyze. In fact, that together with Würzburg and Hamburg, we have been analyzing in the context of dynamical mean field theory. Let me tell you a little bit about this model. So how does this model work? So the point is that we know that there is a model which is in fact describing very nicely the physics of the the magic angle twisted bilayer graphene, which is the Bistritz-McDonald model. However, this model is a model done in the continuum. It's a topology. It has it's heavy topological. So there is the band inversion at the gamma point. So the problem is that if you want to describe correlated physics, you need to have a lattice model. You need to have states that you can define as your localized states. So the problem with this model is that you cannot do this transformation to a lattice state due to the topology. So what the proposal of Sida and Andre was, well, what we are going to do is to define a basis of Bannier functions that in the gamma, at the gamma point, where we know that there is this band inversion, what we are going to do, also what they have done, is we borrow the topology of the C bands that are here, the neighboring C bands. We borrow this topology at the gamma point, and then we can create a basis of Banach functions that will allow us to write down this lattice model. And this is what they did. So they defined this basis, and then they project the Bistritzer-McDonald model on this basis. And what you obtain after this projection is indeed a lattice model. So in fact, this is the basis, in fact, are very well behaved, as one would like to have in a lattice model, that they indeed, they fall down in an exponential form. And you can see that they can recover very well the Bistritzer-McDonald model. This is now the put on top of the model. What is this lattice model doing? So let me just describe this lattice model. And when you look at it, indeed, it looks like a heavy fermion type of model. So what does it have? Now we are going into the language that these flat bands, we are going to call them, in the language of heavy fermions, we are going to call them the F bands, and these are going to be our C bands. So now what we have here is a Hamiltonian that contains, of course, the kinetic energy of the C bands, the hybridization between C and F, Coulomb interaction between the F bands. So the F bands are, of course, very flat, strong correlated. And then, of course, we also have CF density type of terms, as well as a density term in the C electrons and the CF exchange term. So now this is a model which, let's call it topological heavy fermion model, which has extra terms that are not seen in a heavy fermion model, but looks very similar. So now what we want to do is to understand, or at least to analyze, how far this model describes indeed the experimental observations. And so you see that we have many interacting terms here. So what one has to do a selection of which interactions do you want to treat at the level of mean field, and which interactions you can go beyond that and include even dynamical correlations. And this is what we are doing. I have to see, where is Valentí is there. I have to see your sign. And this is now the way that you have to decide, in order not to harm the system, how far can you go in your approximation. So the way, one of the best ways to do that is to treat these terms in a mean field type of, at the mean field level, and to treat the FF density terms, so the Coulomb repulsion of the F orbitals, dynamically. So that means that you have two self-consistent type of equations that you solve together. So what does one find out? Or so let's say, what kind of aspects or results do you get, one does get out of the analysis of this type of Hamilton? So let me show you here, for instance, what I'm showing is the spectral weight at omega equal to 0, which means at the Fermi level, as a function of the doping. So this would be the neutral. So this is at 0 doping, so which would be in our language the half-field case. So at 0 doping, so if you look, this is 0 doping, -1 and -2. What happens at these integer dopings is that if you look at the spectral weight, here it's resolved in terms of the C electrons of the F electron. There's a strong depletion of spectral weight exactly at integer levels, while as soon as you go away of the integer level, you see a very important weight. So there's a very important weight at the Fermi level. It means that you are in a metallic state. So you can find kind of almost insulated to metal behavior going from integer filling to fractional filling. And in fact, the dope charge, if you want to see where the dope charge is going mostly on these F bands, but there is a game, thank you. There is a game between, in fact, there is a redistribution of charge between this localized F band and the C bands. So, and this is going to be very important in order to describe what is happening experimentally. So let me also investigate the screening effects. So the screening effects that one can now analyze at the different fillings. So again, doing the same type of calculation that we did for the previous case. Here, what I'm plotting is T times chi. So that means if it's flat, it means that it really follows a Curie behavior, and therefore the moments are non-screened. And this is what is being observed at the fillings that are integer fillings. So at integer fillings, these are the integer fillings, basically there are on-screen states, which is in agreement with the fact that one is observing an almost insulated state, while for the fractional fillings, there is a deviation already at high temperatures of this Curie bias. So there is a screening which is telling you that we are in this metallic state. So a way now of seeing what exactly is happening in the system is by looking indeed at this spectral function resolved in energy and also in K-space. And here what I'm showing is in the system at high temperature, which is called the symmetric phase, there is at a critical temperature, there is a phase transition into a symmetry broken phase. And there is a lot of discussion about different types of symmetry breaking the system. Here, what we considered for these calculations are these Kramer's intervalley coherent state, just to show what is happening, in fact, with the system when one goes from the high temperature to the low temperature. So first of all, let me remain for a moment in the symmetric phase and at these integer fillings. So what one observes is at these integer fillings is that there is not, this is not a Mott insulator that one is observing here. There is always an incipient, weight, which is what I was showing to you previously, which is related, in fact, to the topology of the system. So there is at the gamma point, there is this incipient weight coming from this hybridization with the C electrons. However, when you go to the ordered phase, then because of the ordering, the gap is really a gap. We have a Mott insulator at these integer fillings. And here it's just to show that depending on the filling, in fact, which is the distribution of charge at these integer fillings. But now what is more important, of course, is what happens when we go to these fractional fillings. So these fractional fillings, let me stay, for instance, with the symmetry broken phase, where we have clearly here a Mott insulator at this nu equal to -1. And now there is one here, if we go to the left, what we are doing is to put electrons, and if we go to the right, we put holes. And then what one observes is this, what I was mentioning previously, that we have this insulator to metal transition, because as soon as you start doping, you start feeling this let's say the C character of your band. So you have, in fact, a coherent metallic state. However, this metallic state depends, the nature of this metallic state depends very much on the filling. So let's now go to, in fact, larger and larger fillings. What happens then is that you start feeling the F, so this F part of your band. So you are having, in fact, a reconstruction of your Fermi surface, because you are all the time reshuffling the weight between your C and your F. So between your delocalized electrons or states, let me say it better, your delocalized states and your localized states. And this is nicely seen in this type of pictures that can be nicely compared with experiment. And in fact, I have to mention here that tomorrow Anusre data is going to show also DMFT results by considering the multi-orbital projected model from the Harvard collaboration, where these effects are also observed by considering this other model. So the effects that are what I was describing to you is now what I'm showing here is the spectral function. Here is the Fermi level, and I'm showing basically the maximum of the spectral function, where one observes going from this, let me go here, this is what I was showing, this insulating state into this metallic state. Then there is a reconstruction of the Fermi surface, because depending on what we are feeling, and then there is, when we reach almost the next feeling, there is a resetting as it is being observed experimentally in these results from Wong and collaborations. So in fact, this is called a cascade of electronic transitions, and this can be very well understood in terms of this charge redistribution between your localized F states and your delocalized C states. And you can then observe that these are Lifshitz type of transitions by looking, in fact, at the Fermi surfaces. So here are some plots, some snapshots of Fermi surfaces at different fillings, where at high temperature, which would be the symmetric phase, there is a lot of incoherent weight in these F states. So you almost see no weight of this spectral function, while going to the ordered phase, because of the ordering, then the ordering indeed restores some coherence in the state. And as you can see, the Fermi surfaces are very much well defined. So, and what is important, that this was in fact remarked here in this nice work, is that these cascades are observed independent whether you have broken or symmetry breaking or not. So now, of course, we can sort of write down a phase diagram from this model and see how much this phase diagram is in fact in agreement with the experimental observations. So on the top, what I'm showing now, so this is the order parameter. We define an order parameter that is going to be non-zero as soon as we are in the symmetry broken phase, and is zero in the symmetric phase. So if one considers Hartree-Fock calculations, then the temperature, the critical temperature where you go to this ordered phase, it's about 100 K. Now, if you add these dynamic correlations, as in a la DMFT, what it's nice to observe is that these dynamical correlations really push this transitional temperature at lower temperatures, so about an order of magnitude lower. So we go to 10 to 15 kelvins, and there is where the phase transition to this ordered phase is observed. So if we now compare, so we can now schematically write a phase diagram of temperature as a function of filling, defining these different phases observed in these calculations, where we have at low temperatures in the symmetry broken phase, coherent metal at fractional fillings, well-defined Mott insulator at integer fillings. And as soon as we go to the symmetric phase, this is a very incoherent metal, where at these fillings, integer fillings, we have this very incipient, so it's not an insulator because we still have an incipient weight there, which is non-zero. And these ordering temperatures predicted by DMFT are in fact consistent, for instance, with transport measurements, where they see, in fact, a lowering of the resistivity. I have to mention, but I don't have the slide and I don't have the time, I think, that what is very interesting is that this cascade behavior that I was showing to you, these Lifshitz transitions, are also related to the observation of negative compressibility. So we can discuss that later if you want. So with that, I think I can come to my conclusion, because my time is over, that what I wanted to show with these results is that these platforms of heterostructures or twisted bilayer, which by now are being very much investigated, are really a very interesting and plenty of surprises type of platforms to investigate new states of matter. And what is interesting is, for instance, what is important maybe to say when one is dealing with heterostructures, is always to take into account the fact that you have charge transfer, not only hybridization, but charge transfer. And therefore, one should take that into account in order to understand what is being observed experimentally. And in fact, this is, in our view, a new platform for heavily doped Mott insulators on a triangular lattice, where you can start to play and think about, can you get here maybe some kind of topological superconductivity or other type of phases? And in the case of the magic angle twisted bilayer graphene, this is indeed seems to be a new platform for heavy fermion physics. By using the topological heavy fermion model, by analyzing it, many of the features that are being observed experimentally seem to be included in this type of models. And therefore, I think that this is also a very nice description to bring together heavy fermion physics into a new platform. And I think my time is over. I thank you for your attention. I am happy to answer questions.